So this is a facility that's just sitting in an unassuming little corner of Denver, Colorado, which is sponsored by the National Science Foundation, where it's cold storage with a whole bunch of these metal canisters. Inside each one of those canisters is one of these. This is an ice core. And so these are retrieved by Greenland or Antarctica, somewhere where there's a thick ice sheet that is built up over many, many years, and drilling down into the ice and pulling out a plug that looks like this. And you can see that it's made up of a bunch of layers. Those are like the rings of a tree, where each one of those layers is 1 year of snow that fell on, in this case, Antarctica. And then the next year, snow piled on top, and the next year, snow, and it packed down and compressed and became ice over time.
So why is the color difference? Like the periodic color?
Density is the main reason.
Where is the periodic? Yes, animal. That's white, black. White, black, white.
That might be a coincidence for that particular region, but it's a good question.
It's not there.
So what's cool about these ice layers is that just like the ice cubes that come out of your freezer, there's bubbles inside the ice. And the air that's in those bubbles is the actual air that was on Earth when that snow fell on Antarctica, and it got trapped all this time. And the deeper you go down into that ice core, the further back into time you're looking. So the deepest ice cores we have go back 800,000 years into the past, where we have the actual air that was on Earth each year, going back hundreds of thousands of years. And so these are the data of the carbon dioxide concentration in the atmosphere just for the past 1,000 years. I didn't want to go back all 800,000, which we have the data for. This is just the past 1,000 years. And you can see that just naturally there are slight variations in the amount of carbon dioxide in the atmosphere from year to year until something happened roughly around the year 1800. And what happened there was us. This was the Industrial Revolution. We started burning fossil fuels, which released carbon dioxide into the atmosphere, increased. And there you can see the data. It started skyrocketing. Well, in the last, 70 years or so, since the mid-50s, we've been collecting direct samples of the atmosphere every day. So prior to 1958, we have data year by year for hundreds of thousands of years, but since 1958, every single day. And here's the data from 1958 from that observatory. Again, you can see the trend of carbon dioxide is continuing to rise. Now that we can see with daily resolution instead of annual resolution, there's also a wiggle on the data, a small crowd. Anyone know why there's a wiggle? Photosynthesis. This is the Earth breathing. Like life, plants grow through the spring and summer, sucking carbon out of the atmosphere, and then they die off in the fall and winter, releasing that carbon back into the atmosphere. So it's just a cycle, goes up and down. Now, you guys are smart. You might say, why northern and me, you're going to ask. The difference is there's more land in the northern hemisphere than in the southern hemisphere, so it doesn't exactly balance out across the year.
It also tells you how much plants can consume.
That's right, yeah. It's also a measure of kind of the carbon content of plants. That's right. Other than the ones that are there all the time. So, but the wiggle is just reversible, right? That's just every year. The background signal is still climbing because we're continuing to burn fossil fuels and release them in the atmosphere. And to get a better sense of the scale here, let me just squeeze those two plots together on the same scale. And now you can really see how dramatic the increase in carbon dioxide concentration has been. Way beyond anything seen, not just in the last 1,000 years, but actually higher than the entire ice core record, going back 800,000 years. It has never been during that period as high as it is today.
So can you see the effect of deforestation, or just too small a thing?
Well, I mean, I guess, this is the total carbon in the atmosphere, total carbon dioxide in the atmosphere. So it would be from all effects, but the increase in carbon dioxide is there's an isotopic signature.
So that major equilibrium, somebody has to write. It didn't change, right? The fossil fuels, they say it's good for forest.
So that's actually one of the myths is that, in my book, if you're interested, that carbon dioxide is plant food, right? And so this will be good for plants. It turns out that actually that's not necessarily true. People have done these controlled environment studies. So if you're house and you just pump in a little carbon dioxide, it is good for the plants. But that's not the environment plants live in. They're out in the open world. And it's actually not necessarily even a net positive for plants. There's more carbon dioxide in the atmosphere, but it's certainly not a net positive for us. Okay, so that increased carbon dioxide because of the greenhouse effect leads to warming. Temperatures started rising. And the temperature goes up, ice starts to melt. This is Greenland ice sheet, ice mass going down, where that ice is getting dumped into the ocean, and the ocean itself is also expanding because of thermal expansion, so the sea level is rising. Anyone who tells you the trends, that it's not clear what's happening, it's pretty obvious what's happening. So there's a sequence that I'd like to walk us through because we're going to work forward and then we're going to come backwards because we want to start thinking about what we can do about this. So what's happening is we're emitting carbon dioxide. That is leading to an increase in the concentration of carbon dioxide in the atmosphere. That leads to warming, and warming has consequences. So let's keep that whole sequence in mind. I'm going to keep coming back to that. But let's just start. If you're in the room, I'm assuming you're well aware that there are serious consequences for climate change, and they're not good. I won't take the time to walk through all of these because I think that might be preaching to the choir. We're having droughts that haven't been seen in the American West in more than 1,000 years. Just down the road in Norfolk, Virginia, sea level rise is showing up in significant flooding of homes and on and on and on. So what can we do about this? There's basically 3 strategies that we can use to tackle climate change: mitigation, geoengineering, and adaptation. And I'll start with adaptation. And what we're trying to do when we're adapting, steps in that sequence. It's not doing anything about the warming, it's just trying to make the consequences not for us. That's what adaptation is about. And what do we mean when we say adaptation? There's things we can do, and we are starting to do. You can plan for impacts. You can start moving communities outside of flood zones because 100-year floods are now happening every year or every other year in some communities. That is not a place for people to be living anymore. We need to move those people to new regions. That's planning for impact. Build resiliency, build seawalls, elevate homes, for example, when you're talking about flooding or sea level rise as examples. There's other ways we can build in resiliency to our electrical grid. Well, improve response capacity. There's going to be more significant storms. We need to be prepared to respond when those significant storms come through. But the bottom line of adaptation, we have to do all of those things. We have no choice. But you can't adapt your way out of climate change. It's necessary, but it's very far from being sufficient. So next category is geoengineering. And this is something, when I started giving lectures on climate, even 10, 15 years ago, this was crazy to talk about geoengineering. This was like the wild science fiction ideas, but this tells you that things have gotten bad enough that we're actually now talking about doing geoengineering. In fact, we probably have to do some geoengineering to deal with climate change. What is geoengineering? It's basically on purpose changing the Earth's climate. Now, we've done it by accident. We've actually geoengineered, right? By releasing all the carbon dioxide into the atmosphere. That was geoengineering. We just did it by accident. Now we're going to have to do some geoengineering on purpose to try and mitigate some of that. And there are many different ideas that lots of smart and creative people have come up with to try and mitigate climate change by geoengineering. I lump them into 2 categories. One has to do with dealing with the sunlight. What causes warming? There's sunlight coming in and there's carbon dioxide trapping. So we have to deal with those 2 things. Let's start with the sunlight. Lots of different ideas to try and get sunlight out there. Some may be what you're doing in this case, or so-called solar geoengineering, is trying to soften this leak. Not doing anything about the carbon in the atmosphere. We're just trying to have that concentration of carbon dioxide not lead to as much warming. So again, working our way backwards. Now, why would you do this? So here's the general idea behind solar geoengineering. Here we're plotting global temperature over time. And today we're sitting roughly here. If you follow that white arrow, that's what's going to happen if we just stay on the course that we're on now. It's going to go crazy, out of control, irreversible, catastrophic, existential type threat to human civilization. There is some temperature, which has an error bar on it, which is viewed as the stabilization temperature, where once we pass that, you can't come back in various ways. That is an irreversible threshold because there are positive feedback cycles, certain things like the tundra. And for example, you can't put that genie back in the bottle once that happens. So we really want to stay below that stabilization, whatever it is. Now, if we're super successful in implementing all the clean energy technologies we've been hearing about through the day, we will ultimately be able to turn this around and bring it back down below that stabilization temperature. But even if we do the most aggressive, even more aggressive than what's in the Paris Accord and the other agreements, it's not enough because there's going to be this window of time where we're going to go up above that stabilization temperature before we can get back down again. It takes time to implement these strategies. And so solar geoengineering is all about this. It's about buying us time while we're dealing with this carbon dioxide that's already in the atmosphere, and we're not stopping putting it in there today, to buy us time until we've gone through enough of our clean energy transition that now we can recover and stay below that stabilization. So again, something that used to be considered crazy, but people are now not only taking this seriously, but it may be something we actually have no choice but to do. Although, this is what I envision when I think about solar geoengineering. I asked, we were talking about ChatGPT on the way here, but DALL-E 2. I asked DALL-E 2 to draw me a crazy weather machine. That's what that is. That's DALL-E 2's vision of a crazy weather machine. This is what we would need. Maybe all over the planet, maybe only around the equator, some people are saying, but pumping, for example, aerosols up into the atmosphere, try and change the radiation balance so that more sunlight is in space. Sounds crazy, but we're probably going to have to do it. Another category of geoengineering is dealing with the carbon dioxide, which again is what's driving the greenhouse effect. And the one that people are talking more and more about is capturing CO2 in the air. Already so much carbon in there. Even if we stopped pumping out carbon today, we would eventually need to pull out carbon dioxide that's in the atmosphere because we're up over 400 parts per million. In the steady state, that would be a planet that would be too warm to live on in the long run. Capture, we're working our way back. Now, this isn't about the emissions, it's about getting the carbon out of the atmosphere to lower the concentration. So it's softening the link between emissions and concentrations. Now, let's see where we are with carbon capture. Just recently, in 2021, this was the largest carbon capture plant in the world. This is an ISEE. And it's called the Orca plant. And it's nice because they can use geothermal energy to run it there. So it's a green energy source. They capture the carbon, they sequester it under the ground. That Orca plant can capture about 4,000 tons of carbon dioxide every year, which sounds like a big number because a ton's a big thing. But that is no longer the largest plant in the world. Last year, the Tata company installed this plant in the UK, which is now the world's largest carbon capture plant. And this plant is much larger than the Orca plant. It's about 10 times larger. That can capture about 40,000 tons of carbon dioxide every year. So progress. But just to put this in context, that's how much carbon dioxide we emit every year. So you can do the math. We would need about 1 million of the copies of the largest carbon capture plant in the world today just to offset what we're emitting. That's not even drawing down the carbon dioxide that's already there. So that's a pretty tall order. Again, though, something we will ultimately have to do. I don't know what the facility costs. I actually don't know what the cost. It's a good question.
And so, where's the money?
In cars. I don't know. We will be building in the United States some large-scale direct air capture plants too, because part of the bipartisan infrastructure law has funding for the Department of Energy to fund the private sector to build. I don't remember how many they're going to build, 4 to 6, I think. Very large plants, and I forget what the metric is. They will be larger than that. So we will have large ones here, but again, nowhere near the scale.
How many trees do you plant?
You can't plant trees. You can't plant your way out of this either, unfortunately. Yeah.
You saw that it's only about 10 ppm.
Yeah.
Oh, so
So there are other reasons to recover our forests, but it's not going to make a big difference in terms of the climate. It'll make a small difference. I like this photograph. This always comes back to my mind when I think about what the challenge that's in front of us. There is no easy solution to climate change. As you're seeing, these are all huge scale, really, really difficult problems. So the one category that's left is mitigation. And when we say mitigation here, what we're talking about is reducing emissions. And this is stopping the problem at its source. So adaptation, the last laying solar and geoengineering, the one after that, carbon capture. But what we really need to do is to just stop emitting carbon, more and more carbon into the atmosphere. And this is really about decarbonization. So how do we get into this mess in the first place? Energy. So this is a plot of how much energy, what's actually the rate at which we use energy worldwide. From 1993, it's data up until 2020, because I haven't updated it from the most recent data, and a projection going forward to 2050. For the experts in the crowd, that projection has changed slightly since the Inflation Reduction Act came out, which will slightly accelerate the adoption of some of these low carbon technologies. Change a lot, because this is global, this isn't just the United States. Here. First of all, you notice we keep using more energy over time.
It's a pandemic.
You're getting ahead of me for sure.
Yeah.
So we keep using more energy. That's been true if you go back much further in time, and it's going to be true for a long time into the future too, not just the window that I'm showing you here. So today we're using 8 or 19 terawatts of energy around the world. By the year 2050, that's going to be more than 30. That's a significant increase in energy use around the world. And this is more or less unavoidable. This is because of development around the world. Here in the United States, per capita, we're not using here anymore. Our population is slightly growing, but we're also getting more efficient. So we're not responsible now for the future energy use. We're certainly responsible for the current energy use. But as the rest of the world begins to develop, that drives this increased energy demand. So unless development's going to stop, this is going to happen. We need more energy in the future. Where does it come from? Today, all those shades of gray are the fossil fuels. That's where most of our energy comes from today. That's probably not a surprise for most of you. That's what got us into this mess. That's where all that carbon's coming from that's in the atmosphere. What might surprise some people is the projection going forward that this is not using less fossil fuels. It's actually a projection that we're going to increase our fossil fuels. Seeing this play out now, especially, China's because they need so much more energy, they're just doing everything. So fossil fuel use, unless we have dramatic change, is actually going to be what it's like in the future, but it is what it is projected. That piece up there, that low pulse and nuclear together, it's going to have to be way larger than that if we're going to get out of this mess. That slice needs to look something more like this, where the vast majority of our energy is coming from renewables and nuclear low carbon sources. So how much energy can we get from these different sources? I've sized these boxes to scale to represent what you could ever get from these different sources around the world. Now, again, since I've got experts in the crowd, don't take the numbers to be precise. There's an error bar on these, but they're ballpark right for how much you're ever going to practically get from any of these different energy sources if you did it everywhere you possibly could. You'll notice they're not all the same size. Point number one, fossil fuels. There was a time not too long ago, we were talking about running out of fossil fuels, running at the end of oil and so on. That's not the problem. There is plenty of fossil fuel out there. We could run on natural gas for centuries, probably. Not going to run out of this stuff. We could power the whole planet on it, but we don't want to because of everything I'm saying. So you can scale up nuclear energy to power the entire planet in principle. But to get to that scale, you would have to build a new nuclear power plant every day from now until the year 2050. Every single day, new nuclear. Significant scale. And we have the renewable energies. You'll notice they're not all the same size. So geothermal energy, for example, is a great renewable energy source. The Earth's crust is really thin, so you can drill down through it and access the heat down below. So Iceland, as I referenced earlier, is a great place for geothermal energy. There just aren't that many places where the crust is thin enough to do it practically. I told you earlier, we use about 18 or 19 terawatts around the world today. Energy mix today, mostly fossil fuels. Today is what it is. We can't change what we're doing today. I have a 20-year-old son. What about in the year 2050 when he's middle-aged? What is the energy mix going to look like? And remember, in the year 2050, we need more energy. That box is bigger that we have to fill. Now it's 30 or 31 terawatts. So what is that going to look like is the question. What's the energy mix that's going to fill out that demand of 31 terawatts? And that projection that I showed you earlier is something like this. And again, depending on who's doing the projecting, the boxes might be slightly different in size, but the bottom line is it's still mostly fossil fuels. Again, that cannot be what the energy mix is in the year 2050, or we're in an awful lot of trouble. So let's just do a hypothetical game. Let's say we got all the wind, all the biomass, geothermal, all the ocean energy that we could. I'm going to empty those boxes, those renewable boxes up there. How much is that? It's a lot of energy, way more than we're getting for renewables now. But you notice it doesn't fill the whole box. But if you're also paying attention, you'll notice there's a box I didn't show you in the renewable energy space, which is the solar energy box. So without that, you might say, oh, renewables aren't enough. How big is that solar energy box? So I'm going to move from boxes to circles. So that's a circle. It's just too big to fit on the screen. That's how much energy strikes the Earth from the sun. But of course, you cannot capture all of the energy strike. So I'm just going to do a simple back of the envelope estimate for what can you actually capture from the sun. First thing I'm going to do is throw out the oceans. Not really practical to cover the oceans with solar panels. So scale down to land area, smaller number, but still a lot of energy. And of course, you also can't cover all of the land area on Earth with solar panels. What is a realistic number for how much land area we could cover with solar panels? I'm going to say 2%. That's a lot of land area. It's about how much land area in the United States is covered by roads, to give you a picture in your head. So it's a lot of land area, but it's feasible. Much smaller circle now, because we're only at 2% of the land area. 2% of the United States, it looks like in Illinois. I picked Illinois because I live near Chicago. But that's 2% of the area of the United States. Feasible. But there's another problem, which is that solar panels don't convert sunlight to electricity with 100% efficiency. There are fundamental limits in that process. Thermodynamics limits you to roughly 30%. It'd be much more conservative than that. You can buy a solar panel for your roof today, maybe some that's commercially available today. I'm going to be much more conservative. I'm going to say 12%. Very realistic number to achieve as a global average for conversion efficiency. So you can see we're down to a pretty minuscule fraction of that monster circle that we started with. But that tiny little circle, the actual feasible supply that we can access just using solar panels, is that yellow box. So the feasible supply for solar energy is more than 2 times larger than the total projected global energy demand in the year 2050. Now, the point is not that we should get all of our energy from solar. We should not. There are all kinds of reasons that would be a bad idea. But the point is, there is plenty of energy there. And by the way, it's not surprising that solar is bigger than wind, biomass, hydropower. Those are all solar energy. They're just going through extra steps. The wind blows because the sun heats up the air. Biomass is photosynthesis, sun making plants grow. Hydropower, the sun evaporated the water and came down as rain up on a high elevation and we built a dam. They're all solar energy, just going through extra steps. So it's not surprising that solar energy is the larger source to begin with, because even okay, but you might be saying, but isn't solar energy too expensive? It used to be. So if you bought a solar panel back in the 1970s, you were quite, a tree hugger. But it's come down tremendously. Solar panel prices are now so low, you can probably see sitting in the back on this pay under $1 per watt for panels. And by the way, the same is true for wind. Wind prices have come down dramatically as well since the 1990s. And in fact, if you look at what's called the levelized cost of energy, an apples to apples comparison, solar and wind are the cheapest electricity that you can install right now. And most installations for new power production in the United States are solar and wind for this reason. It's just economics, not environmentalism driving it. It's actually a cheaper way to get electricity. which is great news for facing this challenge that we're in. Now you might say, okay, so it's cheap, but what about the fact that it's not reliable? What about when clouds go over your solar panel, or when the wind stops blowing, or it's nighttime? Isn't that an issue when it comes to relying really heavily on things like solar and wind? One important point that not everybody appreciates is that actually at some level, more solar helps itself. And this is in the context of cloud cover, especially because if you have a solar array over clouds may not be over those arrays at the same time. So if they're connected together in a grid, the variability over here gets balanced by what's happening over here. And as you do that, they all average out to basically look like a nice smooth curve of sunlight coming up at dawn and setting at the end of the day. These are actual data from some plants in California showing that to you. As you connect more and more of them together, you get a nice smooth production curve. Now, one of the things we're going to need to take advantage of that is better over large distances in the United States easily. There's a few where you can do it, but not very many. We're going to need a lot more of that, building these large-scale transmission lines to move power from where it's cloudy to where it isn't, or where it's windy to where it is. Now, there is a challenge that gets created as you have more and more solar on the grid. Let me just walk you through it real quickly here. This is a typical plot of what electricity demand looks like on a grid. It's roughly flat until everyone comes home at the end of the day. Well, I guess pre-pandemic, everyone comes home at the end of the day. You turn on your air conditioner, your TV, you start cooking dinner, etc. There's an increase in demand, and then you go to bed and it goes back down to that piece. So that's what it typically looks like. Now that solar production curve looks like this through the day. Again, sunrise to sunset. And as you have more and more on your grid coming from solar, your apparent demand looks like this, where you're producing more than you need. And so there's this apparent big drop in demand in the middle of the day when the sun is shining really brightly. And then worst time of all, everybody's coming home, your demand is peaking right when the sun is starting. And so you're losing your production right when you need the electricity most. And so you get this big mismatch in the timing. And so the shape field of the a little bit like the profile. And in fact, there's now so much solar in certain electricity markets, like in California, for example. You have a question, I'll get to it in 1 second. And it's actually now getting called the canyon curve. It's so deep that it drops all the way down, and you don't see the peak on the other end. It's just a grid operators. You had a question?
Doesn't can't solar store energy though that it
Good question. So the solar panel can't store it, but there's another way to do it. That's exactly what I want. So you're perfect. It's like a plan of the question. Solar plus storage. Same applies for wind. So this is really your solution to this challenge. Is storing the energy when you have excess energy so that you can pull it out later. And there are lots of ways to do this. Some scale today is batteries. People are starting to use lithium-ion batteries. The lithium-ion batteries for electric vehicles, after they're no longer good, work. They just don't have quite as much capacity anymore. This is a second life for those batteries. So we were talking earlier about recycling. Before you recycle them, you put them into this life, and then years later, then you put them about recycling. So that's one idea. But lithium-ion batteries only buy you up to about 4 hours. So it's perfect for the duck curve because it can shift you that little bit in the day. But if you're cloudy for 3 days in a row, that's not going to help you. But there's lots of other ways you can store the energy. You can compress air and then turn basically turbines as you release it back out. This is actually in Virginia. That's the Bath pumping station. This is a pumped hydropower storage. You basically have water at a high elevation, water lower down. You have a dam, you can generate hydroelectric electricity. And when you have extra energy, you just pump the water back up again. And so you can just move the water back and forth. That's a beautiful battery, works great, but only in places where the geography is such that you can actually have reservoirs like that. You can also do thermal storage. This is especially useful with solar because you can use the heat from the sun, not just use solar panels to make electricity. And you can store thermal energy for, not forever, but think of giant coffee thermoses basically, where you heat up a fluid thermally insulate it, and then 8 or 12 hours later, you can get that out as electricity. And then if you really super long time, you do chemistry, you make chemicals, you can make hydrogen or ammonia or other chemicals that can store it more or less indefinitely, and then extract the energy. So this is where our greenhouse gas emissions come from in the United States. And it looks a little bit different when you look at the global numbers, but all same idea. Everything I've been talking about is really about tackling that slice of the electricity production. And as we have more renewables and nuclear, we're going to decarbonize that part of our emissions. I'm going to help a little bit here up in transportation, because as more and more electric vehicles start getting used, we're now replacing fossil fuels with hopefully renewable or nuclear created electricity, decarbonizing part of the transportation fleet, the light duty parts. Unfortunately, all these other parts of the transportation sector, air, rail, marine, heavy duty, off-road, none of those things are going to run on batteries anytime soon. There's not enough energy density in current battery technologies to power something like a commercial aircraft. So we need some other solution for those. It's also not going to help us too much here, at least with our existing technologies. So how are we going to deal with all of this? Well, first of all is efficiency. There's things you and I can do to try and lower our carbon footprint. And there's all kinds of life changes that we can all make to make a difference. And the x-axis here, I think, is reasonably quantitative. The y-axis is probably different for every person. Some things are, some people are happy to eat vegan, and some say they would never do that. So you can kind of be a little fuzzy on the y-axis, but the point is, we can all do some combination of these things. But those demand side solutions are only going to make, again, a little bit of a difference. Just like adaptation, you can't solve the problem here just on those demand side solutions. So we've got some really difficult stuff we have to do. I'm going to play this like 5-second video clip from the movie The Martian. Have you guys seen The Martian? So for those who haven't seen it, Matt Damon is an astronaut in the future who goes on a mission to Mars and he gets stranded there all by himself. And he needs to survive under ridiculously difficult circumstances. And I just love this quote from the movie.
In the face of overwhelming odds, I'm left with only one option. I'm going to have to science the shit out of this.
That's what we're going to have to do here, science the bleep out of this. So how are we going to decarbonize these other slices of the pie that we can't do with just having solar engines? So the yellow piece there, the commercial and residential slice of the pie, that is from heating and cooling buildings. That's the biggest chunk there. And so if you're using a gas furnace, that's releasing carbon into the atmosphere. I have a gas furnace, unfortunately, in my house. This is the logical solution. That is a heat pump. Heat pumps use electricity, so it can come from renewable sources because it's electric. Just moves heat back and forth to either do heating or cooling, depending on the season. Now, the reason we need to science the bleep out of this is that current heat pumps are pretty expensive. They also don't work in super cold regions. There are various challenges with heat pumps, so we need to do additional research and development to improve the technology. How about the industrial slice of the pie? We need to electrify the major carbon emitting industrial processes. That's ammonia production and steel production are two of the biggest ones. And there are ideas on how to do this. They, in principle, could be electrified, but it's a different process. We need to do more research and development to optimize that. What about all those other parts of the transportation sector that we can't electrify? So again, air, rail, marine, off-road, heavy-duty road. We need fuels because they're more energy dense, but we don't want them to come from fossil fuels. So we need what we call low carbon energy carriers. That could be hydrogen. It could be ammonia. For aviation, it could be what are called sustainable aviation fuels, biofuels. So as long as your fuel doesn't release a lot of greenhouse gases in its production or use, it's a way to decarbonize those other sectors of transportation. And another big one is cement. So I mentioned steel and ammonia. The other biggie is cement. If you hit those three, it almost doesn't matter. Everything else is so small compared to those three that it's almost irrelevant. So there are lots of great ideas out there where people are looking at how to decarbonize the production of cement, and in fact, even to store some carbon in the cement. So this is my final slide. I love this photograph. This is an actual photograph of the planet Earth, taken obviously from space. That says the sun is just peeking up around the edge of the planet there. And that line of blue you see, it's not false color, that's the atmosphere of the Earth getting lit up by the sunlight. And when, if you go outside and look at the sky, it looks like infinite, right? It seems huge. But when you see it at this scale, you can see the atmosphere is actually razor thin. And when you see it like this, I think it's easier to understand that we've actually changed the chemistry of the atmosphere in a way that it's behaving differently than it has throughout human civilization and long before their emergence. Time to do something about it. I'm happy to answer any more questions that you may have.
Upon is a lot of the solutions you propose, how much energy, additional energy you need, and what is the offset?
Good question. It's almost like a planet. Who was sitting next to me at dinner? You were. We were just talking about this while we were eating dinner. So yeah, PVs is a great example. So let's talk about that since it's your field and now it's a good one to talk about. So talked about the opportunity of solar, but what solar technology, PV technologies are available today? There's silicon solar, the entire market, cadmium telluride, SIGs, next gen ones like perovskites and organics and so on. When you make any of these technologies, you're investing energy into making them because it takes energy to do anything. Then you plug in your solar panel and you start getting your energy back. And you can calculate how long will it take to get back the energy that you put into making the thing. And for silicon solar panels, which dominate the market, in a sunny place, that number is 2 years. Now, the panel's going to live for 30 years or longer, so you'll get back in its lifetime way more energy than you put in. It's not like it's a net loss, but you're going to have to wait 2 years before you get it back in a sunny location. It'll be longer. That's a problem. That will limit how fast we can manufacture the solar panels. If we took all the solar panels that we have on Earth today, used all that energy to make solar panels, and then used all of their energy to make more solar panels and so on, that would not ramp up enough solar panels to combat climate change on the time scale that we need. If time wasn't a factor, it would be fine, but we don't have time. So unfortunately, silicon solar panels are too energy intensive to manufacture. Now, all those other ones I mentioned take less energy, but cadmium telluride uses tellurium, that's rare. SIGs uses indium and gallium, that's rare. Perovskites uses iodine, people don't know that's rare. None of these other technologies also can be scaled to solve the problem for a different reason. So right now, we actually don't have a photovoltaic technology that could be scaled fast enough at the scale that we need to actually make the difference. Now, we're not butting up against those limits yet, so we should be like trying to manufacture like crazy with lower efficiency, lower energy manufacturing process for some new photovoltaic. Is that answering your question? Yeah. Should ask you.
So is fusion the wild card here?
Yeah, so you notice I had like the empty box over there, nuclear fusion. Our fusion guy's not here, right? So if fusion energy were to work, it would be huge. Water is the source. It has basically no emissions, plentiful energy. It's wonderful in so many different ways. No carbon emissions other than just building the apparatus itself. The problem is that it doesn't work today. And the joke in the energy industry is fusion energy is 30 years away, always. And that's actually held true. It's a joke, but it's held true. When I first got into energy years ago, the fusion people were saying they were 30 years away. It's now like 15 or more years later, they're still saying they're about 30 years ago. That's about what we heard today, right? So we should work on it because in the long run, we'll figure it out. I'm convinced we'll figure it out, but we cannot wait for fusion to deal with climate change.
I mean, there are ways to get around, right, using iodine. There's a class of hydride-based perovskites.
Different perovskites.
That do not use iodine. So what's the problem with that?
Do they use cesium? Is it those? Yeah, that's another problem. So, I mean, you need only earth abundant elements and to be efficient to manufacture. It's a pretty tough ask. So organics, in principle, organic photovoltaics might have a chance if you could a molecule you could synthesize in like 2 steps that had high enough efficiency. All the high efficiency organic photovoltaics are like 9-step chemical syntheses. forget it, too much energy and other environmental impacts associated with that. So, I don't want to be like a downer. It should be something exciting for researchers to work on. This is a problem. Sure, it exists, right? Out there in nature, there is some material in principle we could make that wouldn't take so much energy to make and give us enough efficiency that it would work. So we found it.
Yeah, just comment on that one. Have not run out of any element yet, but the price goes up.
Yeah.
It becomes rarer,
That's
and
right.
then automatically people switch to something else.
Yeah.
So, for example, look at catalytic converter in car. How much?
Yeah.
And it's all recovered back and it's like.
There are additional complications, like tellurium is a good one. Tellurium is not found as a pure element out there in Mother Nature. It's out there with the other things like copper, for example. And so to get more tellurium, so it's actually pretty cheap. You don't need a separate operation to go get it. If you want to make more tellurium as an increased resource, you would have to mine more copper. And you would have to mine a lot more copper because the tellurium is an impurity. And nobody's going to go out there and do something at a 100 times scale to get this little thing as a byproduct. It would make no economic sense at all. There's a question.
Storage. The car batteries before they're taken out of the car, B to G.
Yeah.
How promising is that? I've been hearing about it for years, but
So
let's scale that. And the other thing is energy vault type and gravity battery.
Yeah. That's another way to store. Yeah, I could have had a little picture of that too.
Yeah.
So let me answer the first one about the B to G. So generally, the sectors of the economy are becoming more and more interdependent. Vehicle to grid is one of the most examples to get. As we have more and more EVs, there's a demand change because now we have electric vehicles at some time of day, and that leads to a spike in demand, which will grow as there's more and more EVs. So that's one direction. But you mentioned the other opportunity, which is that all those batteries and all those electric vehicles could be a stabilization resource for the grid.
With all their solar in California, if you plug in wherever you are during the day, work, home, wherever, school, and charge that up, and then get home for the head of the duck.
Right. So
at least be the H.
So the challenge with this is partially consumer psychology. That I don't want you telling me when I can charge my EV, and I don't want you taking my electricity. What if I decide to go out for a late snack and now my car battery's dead to go where I wanted to go or
It'll
something?
have to be the challenge.
Yeah, so there's challenges about doing it at scale the way. I think the bigger opportunity is when we start having more and more EV buses and things like that, school buses, city buses. Those are sitting dormant for long stretches of time, and they're much more predictable, and it's not a consumer choice issue. They can be used for storage on the grid.
Dominion has a pilot program where they help certain localities get electric buses, and they're trying that out.
Great.
Using storage and
Great.
gravity batteries.
Yeah, so it's another way to store energy. Again, it's going to be limited in scale to some extent, but it all comes down to cents per kilowatt hour that you can store.
In the mitigation, you basically said that the rail and heavy trucks and so on, that's not feasible with electric, and I'm wondering why.
Energy density. So batteries don't store anywhere near the energy density that a chemical fuel does.
But rail, basically the electricity could be provided as it's going. So it was very interesting. A few years ago, I went to see a Formula E race.
Yeah.
And at that time, halfway through the competition, they had to change the cars because the battery could last just half competition. Now they don't have to change cars anymore because they put a pad, and the cars, as they're running over this pad, are charging.
So
would that be a feasible way as roads, highways are repaved and so on to actually?
I know where you're going, and Judgy, I hope I don't offend your ex-colleagues in Oak Ridge, because Oak Ridge has been trying to pitch this.
The wireless charging, obviously, the amount of magnets and things you need is humongous. So I think the general comment is that if you want to accelerate decarbonization, as I said in my talk, the speed and scale, the storage is the weakest link. If you estimate whatever Seth said is all right, generation, the levelized cost of electricity for generation is almost 0 cents. Generation is not a problem. If you really extend the slope, solar and wind, you can see as the Texas fault, huge, but the weakest link is the storage. And then if you meet those goals, the amount of battery storage you need at the cost you need is humongous. So I think part of the thing is, again, boils down to the storage. How can you store and use that storage when you need, whether it's industrial decarbonization or any kind of things. Yeah. So storage cost has to be reduced, and where will we get all those batteries for those things?
Grid storage, vehicle storage have different requirements. Vehicle, you need it to be light because you're very but on a
Round trip
grid,
efficiency is very bad.
heavy.
Round trip efficiency.
Right, so it's different requirements, so totally different technologies. So
lithium ions.
material limitations and cost for in-road charging, if that's what you're. So yeah, per mile of road, astronomical. In the day, they used to talk about solar roads too. I don't know if you remember that. They used to talk about like turning roads into solar panels, which is the stupidest idea. First of all, it'd be too expensive. Second of all, they're going to get filthy in like a week and stop working entirely.
So that is one of the biggest problems with panels.
Dust. Yep.
Birds dropping.
Yep.
You have to keep it clean out there.
Creating the solar panels is a challenge. So for the students, you have materials research, having surfaces that provide self-clean is an opportunity.
So you have to do solar tracking, right? I mean, something has to move with the sun.
Well, you don't have to. So it's a trade-off, right? You're going to pay money for mechanisms that will do that, or passive mechanisms that don't do it as well. But you're going to gain some efficiency, right, by staying pointed at the sun. And it comes down to the cents per kilowatt hour you have to do math, especially if parts fail. So you got to do life cycle. How many cents per kilowatt hour are you going to get? Most arrays these days do not track. So the economics work out that it's cheaper not to.
So was it because they have to do mechanical motion?
Yeah, so I've seen like passive technologies that rely on thermal change. So kind of like a fluid that maybe warms up and expands and kind of moves. So it doesn't point directly at the sun, but it moves roughly in the right direction over the course of the day.
Why can't you just use a prism?
I'm not sure I follow.
A prism. So if you just use a prism, I mean, you can collect light from different angles.
Redirect the light. Just redirect the light.
Yeah. So, I mean, whether you're incident from here or from here, whether you're incident from the east or from the west, you'll concentrate.
Yeah, that's already been done for CSP system. Concentrated solar power, where you use the steam, focus always.
Just I can see a small receiver. I'm not picturing the geometry of which
So that's
Hey, you want 22 cents per kilowatt or
doesn't cost that much.
you can imagine for the entire area.
I don't know.
Yeah, one small cell, yes. Considering an entire area, how many things?
I didn't think that prisms cost that much.
But that's on an entirely different scale. There is this prediction in the Hindu scriptures that we are heading towards what is called proloy. Means the total devastation, where the entire world will be filled with water. And then everybody will die, and then a new cycle will start. So it is just a cycling that's going on. And so are we heading towards
sea levels rising. Yeah. So I mean it takes ice a long time to melt. So time constant for that is incredibly long. The carbon that's already in the pipeline will melt most of the ice eventually, but it's like your great grandchildren will be dead by then. So don't worry about that. But if we keep emitting though, It accelerates,
Yeah.
right? So yeah, we're getting there, and sea level's gonna rise. What we do, sea level is gonna continue to rise for a long time. And real estate on the coast. Terrible idea right now.
So if the ice is going to take that much time to melt, we have that temperature, so why do we need that time to set? Like we're checking off the sun's like.
So it's rising already, right? It's gone up, sea level has risen 8 inches.
Yeah, 4 millimeters.
Right,
Yeah.
yeah, so it's that all of the ice take centuries to melt, millennia maybe.
But even if a fraction melts, it's enough to cause coastal flooding.
Yeah, well, it's happening already. It's already gone up 8 inches and is rising.
So is there a number like we are 8 inches, like if it goes from 8 inches to 12 inches on the coastal towns?
There are some beautiful visualizations you can find online with sliders, where you can go around the world and move a slider, and it'll show you based on the elevation maps, kind of what would flood for different levels of sea level rise, and it is shocking. You have to remember that a huge fraction of humans live very. It's, New York, Miami, Cairo, yeah, most of the Southeast Asia,
Venice,
London,
Venice.
yeah, I mean, just all over the world, huge cities end up underwater.
I have a coffee mug.
Coffee mug,
The hot liquid.
that's a depressing comment. I don't drink out of that every
You
morning.
didn't mention, serious question. You didn't give any mention of ocean acidification.
Yeah.
Yeah. How serious is that considered?
It's a huge problem. Yeah. So for those who don't know what he's talking about, as we release carbon into the atmosphere, it doesn't all stay in the atmosphere. In fact, most of it doesn't. Sucked into the oceans that dissolve it.
Little bit.
A lot. It's a lot.
Yes, still I'm just saying, compared to what we release in a small fraction. Otherwise, we wouldn't have seen it.
It's a good amount, but the soil also captures some. But it's what happens is when you put carbon dioxide into water, you get carbonic acid. So the ocean is becoming more and more acidic with time, and that all kinds of things, especially if you're a shellfish or a coral, because you basically dissolve. And so, yeah, coral reefs around the world are bleaching, partly from that, also thermal, but just the fact that the ocean's getting warmer and also damaging coral. Oyster populations are starting to plummet in different places. Shellfish that use, calcite chemistry. So it's a problem. Yeah.
Well, it's almost 9 o'clock, and I'm sorry that my colleagues did really miss a wonderful talk. Thank you very much. See you tomorrow morning at 9 o'clock.
Okay.